Problem number 16. A very large number of small particles forms a spherical cloud. Initially they are at rest, have a uniform mass density per unit volume ρ0, and occupy a region of radius r0. The cloud collapses due to gravitation. The particles do not interact with each other in any other way. How much time passes until the cloud collapses fully? The constant 0.5427 is actually a square root from 3 pi over 32. Solution. This problem is about dimensional analysis. And here we already have in the expression square root from g ρ0 in denominator. So we can represent answer in form of time equal this expression, and we have to find what is power alpha. Let's represent our parameters using dimensional analysis. Here we represent all dimensions for all parameters, like time is t power 1, gravitational constant has this representation, density has mass power 1 over L cube, and the radius is L power 1. Now we can put this expression to this equation. Now our equation look like this, and from here we can find what is the alpha. For distance dimension we have this equation. It means that alpha equals 0, and the correct answer is D. Problem number 17. Two small equal masses are attached by a lightweight rod. This object orbits a planet. The length of the rod is smaller than the radius of the orbit, but not neglectable. The rod rotates about its axis in such a way that it remains vertical with respect to the planet. Is there a force in the rod? If so, is it tension or compression? Is the equilibrium stable, unstable, or neutral with respect to a small perturbation in the angle of the rod? Assume this perturbation maintains the rate of rotation, so that in the co-rotating frame the rod is still stationary but at an angle to the vertical. Solution. Let's analyze this motion. Because the gravitational force goes as back proportional to r square, the inward force on the inner mass is greater than the inward force on the outer mass. On the other hand, both masses have the same angular velocity, so the centripetal acceleration goes as proportional to r, and the outer mass must be subject to a greater centripetal force than the inward one. So the rod must exert an inward force on the outer mass and an outward force on the inner mass. Thus the rod is in tension. Second, the stability of the position is best understood in the coordinating frame. In this frame the outer mass experienced an outward radial force and the inward tension of the rod, and the inner mass experienced an inward radial force and the outward tension of the rod. When the rod is rotated slightly, these forces create a restoring torque, so the equilibrium is stable, and the correct answer is B. Problem number 18. 2-point particles, each of mass 1 kg, begin in the state shown in the upper left corner. The system evolves through internal forces only. Which of the following could be the state after some time has passed? Let's analyze these pictures. So here on the first picture we have total momentum is 0, center of mass is not moving, and we have rotational momentum equal 2. Let's analyze other pictures. Picture A. Here we have center of mass is in other point, not 0, 1. It's in point 0, 0. So that's not good. Picture B. It has non-zero momentum. It's no good. Picture C. It has angular momentum less than angular momentum in the primary picture. Picture D. It has angular momentum greater than initial angular momentum. And picture E, it has the same position for center of mass. It has 0 momentum, and it has same angular momentum. So the correct answer is E.